So let's continue. It is my pleasure to introduce Chris Jarzynski, distinguished professor at the University of Maryland in various departments, chemistry, biochemistry, and physics. Chris did his undergraduate studies at Princeton University, but took his PhD at the University of California at Berkeley in 1994. After postdocs at several universities and institutions, he became professor at the University of Maryland in 2006 with a tenured track, and a full professor in 2010. Chris is a renowned expert in non-equilibrium thermodynamics and statistical mechanics. And he is in particular very well known for his equality, the Jarzynski equality, which is a very surprising connection between irreversible and irreversible processes and equilibrium quantities. Namely, it is a formula which tells you that you can compute the free energy difference between two equilibrium states by looking at a sort of a path integral in the space of non-equilibrium processes and simply looking at the work done along each of these paths, and that will give you this free energy difference. I must say this was always to me a very surprising result, and he found it in fact 3 years after his PhD. It's from '97. For his work, he has received much recognition. The Sacher Prize, which is awarded to young scientists below the age of 45. And in 2019, he received the prestigious Lars Onsager Prize. He has been a member of the National Academy of Sciences since 2020. And we look very much forward to hearing his lecture today about quantum superimpulses. It's a very interesting title. And so, Chris, please, the floor is yours.
Thank you very much for the introduction. By the way, since you mentioned the Sacher Prize, I wasn't the only one to get it that year. In fact, I remember there was a young Christoph Delago who also won that at the same time. In fact, let me begin by thanking Christoph and all the people at ASC for putting together this very wonderful meeting and for inviting me to it. It's a real honor to be here to help celebrate the 30th birthday. So happy birthday, ASC. I'm not going to sing today. Okay, so the title, as you can see, is Quantum Superimpulses, the title of my talk, and I'm going to be discussing a class of solutions to the time-dependent Schrödinger equation, which I thought was appropriate at the Erwin Schrödinger Institute. And one thing that I find interesting about these solutions is that they are built entirely on classical trajectories, even though I'm not going to ever be taking some semi-classical limit in which h bar goes to 0. So let me just kind of jump in and start with kind of looking at a very, very simple case. And this is going to be, first let me do the classical case. Imagine a particle in one dimension that's subject to a uniform time-dependent force. Uniform meaning it's not dependent on space. Let's imagine that this force acts only over a very brief duration between time 0 and epsilon t, where epsilon is going to be a small parameter which will tend to 0. And let me imagine that the strength of this force scales like 1 over epsilon. And this is what you'd find in an ordinary kind of introductory textbook discussion of impulses, right? So you have a force that acts very briefly, but is very strong during that time, as shown over here. So it acts over a time interval that scales like epsilon. The strength is 1 over epsilon. And then, as we all know, what happens is under Newton's laws, the net effect of this force is the following. The particle's position does not change as a result of this impulse, but its momentum gets changed by an amount delta p, which is just the area underneath this integral. So this is very introductory classical mechanics. But now let's consider what happens if the scaling is slightly different. So I should say, in phase space, what's happening is the position isn't changing, the momentum gets a kick. Now suppose that I have a different scaling, namely the strength of the force is going to scale like 1 over epsilon squared rather than 1 over epsilon. The duration is still proportional to epsilon. And let me now add this additional condition that the force is what I'll call balanced, namely the integral, the net integral is equal to 0. So this looks something as follows. The integral under this curve is 0. The duration, again, scales like epsilon. Now the magnitude or the strength of the force scales like 1 over epsilon squared. In this case, if we again plug things into Newton's laws, do the calculation, we find that there's kind of a complementary effect, namely the momentum of the system doesn't change from before the impulse to after the impulse, or super impulse, but the position now changes by a finite amount, and that finite amount is given by this very simple formula. Again, and this comes out in this impulsive limit, epsilon goes to 0. So when the impulse scales like 1 over epsilon squared, I'm going to refer to that as a super impulse. Now let's look at what happens when a quantum wave function undergoes both, first of all, an ordinary impulse and then a super impulse. Again, in phase space, this is what's happening. For a wave function, typically we don't talk about forces, so instead let me rewrite it as a time-dependent potential, which is just minus x times this force. When the force scales as follows, namely as an ordinary impulse, you wouldn't be surprised to find what happens to the wave function. Namely, it picks up this phase, e to the I delta px over h bar. Here, psi I is the wave function just before the impulse, psi f is the wave function just after the impulse, and the delta p here is exactly the same as in the classical case. Again, not particularly surprising. Effectively, the wave function is boosted in momentum. Its probability distribution in space doesn't change, but there's a boost in momentum. Okay, what about a super impulse? Again, this is the force as a function of time. Here I've sketched what the wave function looks like before the super impulse. And here what happens is that one can show, and I'm not going to go through the derivation, that in the limit epsilon goes to 0, the wave function immediately after the impulse is displaced from the wave function before the impulse by, in fact, exactly the same amount as as in the classical case. So the wave function begins here. After the impulse, all of a sudden, it's over here. All right, so this is a sudden translation. So at least for this very simple case of a uniform force, we can think about it this way, that an ordinary impulse, which scales like 1 over epsilon, effectively kind of paints a phase onto the wave function, whereas a super impulse deforms the wave function. In this case, the deformation is very simple. It's just an ordinary translation. I'm now going to be interested in looking at what happens for more complicated forces, so not necessarily just a uniform force. But this is a simple example to give you an idea of where I'm headed with this talk. And in particular, I'm not going to be focused on ordinary impulses, but as the title suggests, on these super impulses. So with that introduction, let me lay out the problem a little bit more carefully. So the general case I have, and I'm going to start in 1 degree of freedom. Later on, I'll talk a little bit about multiple degrees of freedom. I imagine a Hamiltonian, a time-dependent Hamiltonian, which has some kinetic energy term, some background potential term, u sub 0. I actually could have made this time-dependent if I wanted to. This u sub 0 will drop out of the calculation, so it'll end up being entirely irrelevant. And then I have this, what I call an impulsive term. So this is 1 over epsilon to the power k, some potential u sub I, which depends on position and on time through this scaled variable t over epsilon. And again, I'll be interested in the case of super impulses where k is equal to 2. It'll be useful to introduce this, what I'll call a fast time variable, tau, t over epsilon. So this just marks the passage of time during the impulse period itself. So tau always goes from 0 to capital T, whereas the ordinary time t goes from 0 to epsilon t. And let me now just kind of jump to the conclusion, state what the results are both in the classical and in the quantum case, and then go back and try to derive or at least give some motivation for that. So in the classical case, it turns out that if the system evolves under this, this Hamiltonian, then if its position and momentum just before the impulse are given by x sub I and p sub I, then just after this impulse, or I should say super impulse, the momentum is going to be unchanged, and the position is going to be mapped onto some other position, x sub f, which is a function of the initial position. And this x sub f as a function of x sub I is some monotonically increasing function. It's determined by this impulse potential u sub I. And just as in the very simple case, I had to assume this balance condition, namely that the force integrates out to 0. There's an analogous condition that I'm going to assume here, but I'll explain that later on. It's not. It's a little bit more complicated. So you see what happens in the classical case is just for every initial condition, there's a well-defined final condition, x sub f, that's determined by this potential, and the result of this impulse is just kind of to shift to map the position of the particle from its initial to this final position. In the quantum case, and again, I'm kind of starting with the results here, and then I'll give the derivation in a moment. In the quantum case, what happens to the wave function is the following. If psi I and psi f are the wave function just before and just after the super impulse, then they're related as follows. Psi f evaluated at this position x sub f is equal to psi I evaluated at this position x sub I times this factor over here, where the x sub f and the x sub I are related by the same mapping as over here. This factor is essentially a Jacobian. It guarantees that the normalization of the wave function remains the same. And we can picture this change as follows. So I can always write the wave function as the square root of a probability distribution times some phase. So if this curve over here, the purple curve over here, represents the probability distribution just before the impulse, and the one over here represents the probability distribution just after the impulse, then this is the probability distribution that's obtained by transforming this one under the mapping. In other words, if I sample initial conditions x sub I from this distribution, map each one of them onto x sub f under this mapping, then I'll get this probability distribution. The phase at any point just carries over to the phase at the mapped point, as shown over here. All right. So this is what I'm claiming happens under a quantum superimpulse. And so now what I want to do is give you some justification for saying this, and then move on to the case of multiple degrees of freedom. But instead of kind of trying to derive this result, what I'm going to do is give you a prescription for how you would design this impulsive potential given a particular mapping that you want to implement. And by the way, when the wave function undergoes this kind of transformation, I'll say that it's being deformed under this mapping. So when I use this language, the wave function is being deformed under this mapping, all I mean is this equation over here. Okay, so let me provide in some sense a recipe for how to construct one of these quantum superimpulses, and from there it'll be easier for me to describe why it works. So the first step, or I should say the 0th step, because this really defines the problem, is you choose some monotonically increasing invertible mapping, and let me call it mu. This is arbitrary apart from these conditions. So mu takes any x sub I onto some x sub f. It's monotonically increasing. And I now want to design a potential u sub I that will transform this initial wave function into this final wave function by deforming it under this mapping in the sense that I had on the previous transparency. All right, the first step, having chosen this mapping, the first step is you have to design a velocity field, v of x and tau, whose flow evolves any initial point x sub I at tau equals 0 to x sub f at tau equals t. Remember, tau is this fast time variable that marks the passage of time during the impulse interval itself. The dot here is going to denote a derivative with respect to tau. And all I mean by this is that if I start at some initial position x sub I, let it evolve under this first order equation, then at time t, it'll end up at x sub f, where the x sub f is given by this mapping. So one simple way of doing this is to define a family of trajectories, capital X, which are parameterized by initial conditions x sub I, which just essentially linearly interpolate from the initial condition to the final condition, where this function g of t is fairly arbitrary. It starts at g is equal to 0 and then ends at g is equal to 1. And if I construct this family, then the velocity field is just given by this equation over here. I will impose one additional condition, namely that this velocity field vanishes at the initial time and at the final time. And this is exactly the generalization of that balance condition that I had in the simple case where I said that the force integrates over to 0. So this is where this balance condition comes in. And this just implies that in this particular case, that the g dot is equal to 0 at the initial and final time. Okay, and one can, of course, visualize this as follows. So for every xi at time 0, I draw the corresponding xf at time t, which is the xf that's obtained under this desired mapping. And then these trajectories are just these flow lines which connect the x sub i's to the x sub f's. The velocity field is then, of course, just the slope of that trajectory, and I'm assuming that that slope is equal to 0 at the initial and at the final times, as shown over here. Okay, that's step one. The next step, construct an acceleration field from this velocity field. The acceleration field is just given by this equation over here. And just as the velocity field describes the velocity of a particle along one of these trajectories, this acceleration field just describes the acceleration of the particle along this trajectory. And then from the acceleration field, construct the impulse potential u sub I in the following way, namely minus derivative of u sub I with respect to x is just the mass of the system times this acceleration field. So this is essentially Newton's second law. And this is going to define the impulse potential up to an overall function of time. And that overall function of time classically would make would have no effect at all because it doesn't contribute any force. Quantum mechanically, it will contribute an overall phase to the wave function, and I'll get back to that point in just a second. But apart from this kind of overall function of time, this prescription then gives you a recipe for constructing this impulse potential. And now let me try to show you or try to go through the steps or sketch the steps for why this works. So again, we start off by choosing the mapping that we want, construct the velocity field, the acceleration field, and then the impulse's potential is defined from the acceleration field by Newton's second law. So why this works, let me now define a new function s of x and t, which is defined by this equation over here. Partial derivative with respect to x is equal to the mass times this velocity field. By the assumption that the velocity field initially and finally is equal to 0, this function s, initially and finally must be independent of position. Without loss of generality, I can set this equal to 0 at time 0, and then this will be some constant, let me call it s sub f at time t. Again, that's from the construction of this V field. And then it turns out that from this equation, so both the potential and this action-like function s are defined by these equations up to some overall functions of time, some constants of integration. And it turns out that one can adjust these constants of integration so that this final value of s sub f is equal to 0. And moreover, one can then show that, this action-like function satisfies the Hamilton-Jacobi equation. All right, that's a few lines. I'm not going through the details. The next step is to make an ansatz for the wave function. So I'm going to write the wave function in this form. It's the square root of some probability density, as yet undetermined, some phase, also as yet undetermined, times this e to the is, that's this function over here, divided by epsilon h bar. And the tau that appears on the right side here is just the t divided by epsilon. And now I substitute this ansatz into the time-dependent Schrodinger equation that I had over here. And from this ansatz, what I hope to get is some equations that allow me to determine how rho evolves and how theta evolves, and that will tell me how psi evolves. So if I go through that procedure, if I go through that procedure, again, here's the ansatz, I'm plugging it into this equation. If I plug it in, I mean, you can imagine that there's going to be a whole mess of terms. If I then take the limit epsilon goes to 0, I find out that all these terms then give rise to these two equations. One of these is associated with the real part, and the other with the imaginary part of this equation. So it turns out that for rho, we find that the probability density rho satisfies the continuity equation under this velocity field, and the phase theta satisfies this equation over here, which is just another way of saying that the total time derivative of theta along one of these trajectories evolving under the velocity field is equal to 0. Again, going from here to here is just simple algebra, plugging it in, looking at all the terms, taking the limit epsilon goes to 0, and it comes down to these two equations. All right, so if I know the initial distribution, rho of x sub I at time 0, then the final distribution is related to the initial distribution by this equation over here, which is just another way of saying that the initial distribution is mapped onto the final distribution under this mapping U, and that's by construction. That's from the fact that the velocity field generates trajectories that take you from the initial to the final points. So that gives me this expression, and then this one over here just tells me that the value of theta at the final point x sub f is the value of theta at the initial point x sub I, where again the x sub I and the x sub f are related by this mapping that I've chosen. Substituting these back into the time-dependent Schrodinger equation gives me exactly the result I had previously. So this gives a quick derivation, or sketches the derivation for that justifies this assertion that under such a superimpulse, the wave function gets deformed in this way. Okay, those are kind of the algebraic steps. Now let me try to give a little bit of intuition for why this might work. Notice that, again, the final wave function is determined from the initial wave function solely through this mapping mu. And this mapping mu, in effect, describes what underlying classical trajectories are doing. So that, in some sense, in this impulsive limit, in this superimpulse limit, the evolution of the quantum wave function is determined entirely by the evolution of these classical trajectories that are evolving under the equations I had. So this is essentially a classical or semi-classical transformation of the wave function, which may at first glance seem a little bit surprising, because I mean, if we think of the path integral formulation of quantum mechanics, we know that the wave function at the final time and the wave function at the initial time can be related in terms of a sum over all possible paths from initial positions to final positions. We also know that in the semi-classical limit, where h bar goes to 0, only classical paths should contribute. Here I haven't assumed at all that h bar is going to 0. So why do we get this kind of classical behavior? Well, let's write down again. Here's the time-dependent Schrodinger equation during the actual impulse. Let me rewrite this equation by rewrite it in terms of using this time variable t. I'm going to use the time variable tau, which is t over epsilon. So I'll rewrite it in that variable, and then I'll multiply both sides of the equation by epsilon squared, and I end up with the equation that you see over here. I times epsilon h bar d psi d tau is equal to this kinetic energy term plus epsilon squared u sub 0. Again, I've multiplied both sides by epsilon squared plus u sub I. In the limit epsilon goes to 0, this term drops out. And then basically what we're left with is exactly the time-dependent Schrodinger equation for a wave function evolving under this potential u sub I with an effective Planck's constant, h bar effective, equal to epsilon times h bar. So in some sense, this limit, this superimpulsive limit, is mathematically equivalent to taking the semi-classical limit. So once you look at it this way, maybe it's not so surprising that the solution of the quantum evolution is going to be determined only from classical trajectories. So effectively, this limit is the semi-classical limit. Okay, let me go through a few special cases where one can construct this exactly. So first of all, for a translation, this is the case that I discussed earlier. If I choose my mapping to be simply a translation by delta x, and if I go through all of those steps that I described previously, constructing the velocity field, acceleration field, and so forth, in the end, I find out that this u sub I is just minus some function f of t, which is related to, where this function is related to the value of delta x times x. In other words, I just have to apply a uniform force to get this deformation. And this just says that this just repeats what I had mentioned earlier, but I'm saying here that it comes out of that recipe. Another mapping would be just to scale x linearly. So I might want to, let's say, expand the wave function or compress the wave function by some linear factor. Then if you go through all those steps, you'll find out that this potential that you need to add has the form of, it's going to be quadratic. It's going to be proportional to x squared. And then there's some beta of tau here, which is related to how much you want to expand it or compress it. So in this case, the final wave function has the form shown over here, square root of 1 over lambda times psi initial of x over lambda. Okay, so these are two particularly simple examples, and these are actually related to something that's known as scale invariant driving in this field of shortcuts to adiabaticity. So that shortcuts to adiabaticity is a field that's been around maybe for the last 10, 12 years, where the aim is to try to accelerate quantum dynamics, specifically to drive a system from an initial energy eigenstate of an initial Hamiltonian to the corresponding energy eigenstate of a final Hamiltonian without having to do things very slowly. There's a nice review article of these shortcuts to adiabaticity over here, and then the relation to scale invariant driving, which involves translations and or expansions, is given by this reference over here. Okay, but these are very easy. These are both linear transformations. Let me show you an example of a nonlinear transformation. So imagine that I choose this mapping that's shown over here. Here I'm plotting x sub f as a function of x sub I. These lines here are straight lines with a slope of unity, so to the left over here and to the right over here. And in this intermediate region, we also have a straight line, but its slope is greater than unity. And there are two parameters. So this point over here is a, b. This one is going to be minus a minus b. So these parameters then specify this mapping. So suppose I choose this mapping. So what would a wave function look like if it was deformed under this mapping? Well, let's suppose I have a wave function that looks like the blue one over here, where the probability distribution is a Gaussian. Then what ends up happening is that the wave function is essentially kind of cleaved. If you look at the portion of the wave function that's to the left of minus a, that kind of gets shifted over by an amount b, and to the right of plus a gets shifted over to in the other direction by an amount b, or actually by an amount b minus a, and the portion of the wave function then that's in between gets stretched. So the probability distribution after the superimpulse will look like the red curve over there. And then just schematically, if I imagine that before applying this impulse, there was some phase e to the ikx, then after the impulse, the phase would look schematically like this. So this is meant to represent the real and imaginary portions of this phase. Okay, so this is a more non-linear, I guess it's piecewise linear, but overall a non-linear mapping. And when you go through that recipe that I described earlier, you'll find that actually the impulse potential that's needed to bring about this change is the one that's shown over here. It's mg double dot times b minus a times basically a linear term outside a particular region and a quadratic term inside a particular region, where one can get explicit expressions for this C of tau. I'm not going through the details. They're still not published. I was hoping to have them on the archive by today, but they should be on the archive relatively soon. Okay, let me, in the few minutes I have left, let me briefly go through how this extends to systems with more degrees of freedom. And here one has to get into a little bit more interesting math. But roughly the steps are very similar. So start off by choosing an initial and final wave function. So here, x now denotes a point in some d-dimensional configuration space, Euclidean configuration space. Psi I and psi f are initial and final wave functions that I want. So I want to construct a superimpulse that's going to take me from psi I immediately before to psi f immediately after, where these at this point are very general. So once I've determined how I want to change the wave function, the first step is to construct an invertible map, mu, which has the following properties. First of all, it transforms the probability distribution associated with the initial wave function to the probability distribution associated with the final wave function. And furthermore, I'm going to require that this map is the gradient of a convex function. So there's some phi of x that's convex. Its Hessian is strictly positive, such that this mapping mu is the gradient of that function. And this is the analog of the assumption that I made that in the 1D case, I made the assumption that the mapping is monotonically increasing. This is the corresponding assumption in the multidimensional case. And here it's not so obvious that such a mapping exists, but it turns out that it is true, and this comes from a very nice theorem proved by Brenier back in 1991. And actually, for me, one of the fun things about working on this was I had no real understanding or no real experience with these problems in math, a Monge-Kontorovich problem, problems of optimal transport, and it made me kind of learn some very, very interesting math. But ultimately, I use this math only to say that, to be able to assert that such a function, such a mapping exists. Once this mapping is, once we've constructed this mapping, all the other steps are the same as in the one-dimensional case. So I start off with my function phi. From this, I can construct a velocity field that transports initial conditions to final conditions, acceleration field, and then I construct the impulse potential in exactly the way that I did in the one-dimensional case. And once again, the final wave function then is given. Once I've done this, this potential deforms the initial wave function under this particular mapping. Okay, let me go on to my summary slide. So I've been concerned with the evolution of quantum systems under Hamiltonians of this form, where we have a kinetic energy term, potential energy term. This ended up being irrelevant, plus an impulse-like term, where the impulse can be either ordinary, k equals 1, or super impulse, k equals 2. I didn't talk about ordinary impulses, but there the effect of an ordinary impulse is just the natural generalization of the one that I discussed in the case of a uniform force. I spent most of my time discussing the super impulses, and there the claim is that for this use of I, there is a mapping which is monotonically increasing in the one-dimensional case, the gradient of a convex function in the multidimensional case, where basically under this superimpulse, an initial wave function psi I gets deformed into a final wave function psi f, which is where the two are related by this mapping, and that's shown schematically here. So with that, I'll thank you for your attention, and I'll be happy to answer any questions people may have.
So thank you very much, Chris, for this very clear lecture. Questions? There are several. Maybe you.
So thank you. Very interesting. you have to take the limit of epsilon to 0, right? So I imagine experimentally this would be hard to do, and also it would be in conflict with relativity because you would move something instantaneously from here to here. So my question is, what are the timescales that you need to go to for this to hold in a real system?
Right. So this needs to be investigated. I haven't looked at that any more carefully, but you're absolutely right. This is the formal result as a limit would violate relativity and of course not be implementable in a lab. But presumably for sufficiently small epsilon, this is going to be a reasonable approximation. But I don't have any general answers beyond that. And this is where I think, for instance, numerical simulations, maybe a few exactly models will be helpful. But I just haven't done that. Yet.
I would have questions concerning the relations between the map on the x level and the potentials in the Schrödinger equation. For one question, could we characterize the set of potentials which you get by asking monotonicity, and can you invert the procedure? Can you compute the map from the potential?
So that would be the natural thing to say, given a potential, what's the mapping going to be? So generically, if I just constructed some time-dependent potential, which vanished outside of that interval, but was non-zero inside that time interval, that potential would then not satisfy that balance condition. So if I plugged it into into one of these quantum superimpulses, it would diverge in the limit epsilon goes to 0. Okay. Which is just as, in the simple case of a uniform force, I had to assume that the force was integrated out to 0. So that's why I'm actually doing it the other way around, because a generic potential is not going to is going to diverge. If you're asking what constraint is placed on this use of I, that's a little bit more complicated, but you can answer that question by imagining the solution of the Hamilton-Jacobi equation, right? So the solution of the Hamilton-Jacobi equation is this function S, which at time t equals 0, that function S is independent. So if this is space, the function S is independent of position. At intermediate times, it's doing some funny things, it evolves. And at the final time, this function must once more come down to being something that's independent of position. So that's the constraint that the potential U must satisfy. So the potential U must give us that kind of behavior. And the prescription that I gave for constructing that U guarantees that it satisfies that constraint. I'm not sure if that answers what you were asking very clearly, but that's probably the best I can do at the moment.
At the end, you mentioned the three-dimensional case.
Yeah.
Do you have explicit examples for the three-dimensional case?
So 3, actually, that could be more general, a D-dimensional case, but D could be 3. Yes, so 2, so in the paper that will shortly be on archive, there's 2 cases or I can construct, or 2 cases where I can construct things exactly. One involves simply a linear scaling of the wave function along various directions, right? So let's say I'm going to stretch the wave function in the x direction and contract it in the y direction and do something else in the z direction and so forth. So in that case, one can construct this mapping as well. Go ahead.
No, second question is, what about larger Ks, larger than 2?
That's a very good question. As far as I can tell, for Ks larger than 2, the solution is going to diverge. But I haven't investigated that very much, but it seems that then the super impulse, if you want to call it that, would just be so strong that you don't get convergent behavior and the limit epsilon goes to 0.
Layman's questions could be somehow related to tunneling.
I haven't thought about this. I mean, in some sense, this is fairly generic. Although the tunneling is usually in terms of the external potential. So the external potential in this case was this quantity I called U sub 0. And in that impulsive limit, that potential becomes arbitrary. So I can imagine that I have some potential barrier, and I want to apply an impulse, a super impulse that brings the wave function from the left of the barrier to the right of the barrier. I think really what would be happening there is that the potential at intermediate times is so strong that it's pushing it over the barrier. But maybe one could think of that as tunneling.
Since you mentioned homogeneous force fields at the beginning, I think if you have a homogeneous force field, you can tell what happens even without this limit, without the scaling. Isn't that true that if you have a homogeneous field, the probability distribution just follows the classical flow?
Yes, that's right, and that's actually also going to be true, I believe, for so that you're talking about a potential that's linear in x.
Yeah, exactly.
I think it's also true that if you have a potential that's quadratic in x, you're going to get the same thing. So for uniform forces or linear forces, things can be solved exactly, and it is going to be in terms of the classical. But more generally, in the nonlinear case, that it becomes more complicated.
So maybe there is still 1 minute for one question on my behalf. Well, possible applications. You mentioned this speeding up of an adiabatic transformation from one energy level to another. Do you have other example of such concrete applications?
Oh, so in this field of shortcuts to adiabaticity, yes, people have used those to prepare, for instance, for loading Bose-Einstein condensates into particular traps. It's been proposed there. I know they've done experiments on spin systems where you start a spin, let's say in the Z state, you want to bring it down in the X state. You could do that by changing your magnetic field very, very slowly. But instead, you could apply one of these shortcuts to adiabaticity to do this rapidly. And this is being done by some experimental groups. So those shortcuts are being applied. And one thing I should also mention that I didn't hear, I've been talking about the Schrödinger equation, but all of this would apply equally well to the Gross-Podayevsky equation, where you include a nonlinear term. Because basically, again, that nonlinear term during the impulse period is not going to give you any change in the wave function.
Okay, so thank you very much. We are exactly on time.